In this video, we're going to start talking about the possibility of producing fractal curves in SMAS Studio. The video covers an introduction to the idea of fractals, a brief description of them, and then we're going to present some examples of trees, curves that fill the space, and some in the shape of triangles. So let's get started with those examples right now. This is an attempt to draw some fractal curves using SMAS Studio. I'm going to base my graphics on this book called Endlessly Repeated Geometrical Figures from 1987, although the version I have is from 1991. These are the type of programs that are available in that book. These were written in a language called BASIC, that was the preferred computer language of the personal computers of the 1980s. I have to translate them into programming language for SMAS Studio. The main problem may be when you have to use subindices, like in this case. Actually, the statement is all this one, because the vectors in BASIC started with subindex 0 and went on to, for example, this one had 7 elements from 0 to 6, whereas the equivalent vectors in SMAS Studio will start with subindex 1 to 7. And so it makes things a little bit difficult to translate when you have to use subindices and the subindices are based in some formulas. But anyway, I intended to do that, and also got some information out of this book called FRACTALS, FRACTAL. This is written in Spanish, and this also have some of those computer language programs, I mean basic language programs, although these are a little bit more structured in the sense that they use indentation to show where the statements end. So with that, I'm going to get started with producing some fractals. The first fractal curve we're going to present is this H-shaped tree. The program is shown in here, utilizing the mode function and some loops, and building up a matrix that's going to produce the final curve. P is the parameter that controls the level of development of the curve, and the textbook suggests we go up to P equal 9. So start with 1, we get this simple H shape. When we change this to 2, then the H gets twisted 90 degrees in each side and added to the edges of the main line. And that way we're going to continue adding smaller H's at the edges of the previous ones and reduced by a certain amount. So you can see here how we're filling up the curve. For 6, we have the curve being filled up. And this one doesn't take a lot of memory, and so it goes fast. We're going to see somewhere it takes memory. I'm going to go into process for the video and show you the final results. That's for 8 levels, 9 levels, 10 levels. There you go. And so you can see if you follow that particular line, then you start getting to the different levels of the H. That's an example of a simple fractal curve produced with this program in SMAS Studio. Now, let's go for the next one. This one is the structure of a binary tree in the shape of a little tree like this. Okay, so that's for number 1. Here's the program. One of these matrices stacks the center line, and the other one stacks the size of the shape. And so we go here for number 1, change to number 2, level 3. As you can see, the tree is growing by copying that basic pattern into smaller sizes and put it at the top. We go for 5 here. There it is. Now we go for 6. And I have produced a graphic for the 7th level of this fractal curve. A simple example of a tree, a fractal tree that keeps growing in number of branches, but smaller branches to fill up the space. Now let's talk about a triangular one. Appears in the book by Lewiter, page 12, figure 1.4. I tried up to p equals 5, but that took more than 8 minutes. So I produced a graphic, and I won't recommend you do it unless you leave your computer running for a while you go do something else. Here's the program. Because of the triangular nature, it's more complex than the previous ones. And that's going to be the final results. But this is what we do for p equal 1. For p equal 2, then as you can see, it takes a little bit longer than in the case of the H or the previous tree. And so I'm going to pause. That's for p equal 3. You can see how the pattern keeps repeating. This triangular shape gets repeated here, and then in here in a smaller scale, and then in here and all the branches. Let's go for p equal 4. That's for p equal 4. I took a screenshot from a previous running. It took this time more than 2 minutes and 30 seconds, so it takes some time, but you start getting that repeating pattern that's characteristics of fractals. If you go to p equal 5, that's going to take some time. I just let this program running for a while before I took this screenshot. You can see the beauty of this pattern repeated over and over and producing some sort of shape that's like a triangle with a cut-off part in the middle, that cut-off part in the middle here, and so on. This self-similarity is characteristic of fractals. The final example that I have is the Sierpinski sieve or Sierpinski gasket. It's in the Lewiter book, page 13, figure 1.5. Here's the program. Again, it's going to be available for you to download. And I get here the first 2 levels for 1 and 2. Let me run this for 3. It takes some time, not a whole lot of time, but it takes a while to get it going. About 6 seconds. And this is going to be for number 4. I'm going to put a pause and show you the result. Okay, it took more than 30 seconds, and that's the result. You start seeing the triangular shape being filled up. And this is for 3 and 4. This is for 5. This I took a while, about 8 minutes. And I took this screenshot of it. And now the shape of the Sierpinski gasket is clearer. It's a triangle whose middle part has been removed in a triangular shape, of course. And then the remaining 3 corners has a central part removed, and the remaining 3 corners within those 3 corners, and so on and so forth into smaller and smaller scales. Again, self-similarity, a characteristic of fractals, and this way we end up this particular video.